Have you ever wondered how a computer can look at a list of coordinates and tell the difference between, say, a perfect square and a pointy star shape? Well, today we're going to crack open a classic coding problem that uses a surprisingly clever mathematical trick to do exactly that. Okay, just look at these two shapes. On the left, we've got a nice standard square. All the corners point outwards, just like you'd expect. But on the right, see that? There's a dent in it, an inward point. The shape on the left is what we call convex, and the one on the right is not. Our challenge is to write code that can spot that inward dent using nothing but that list of points. So what's the official rule here? Well, a convex polygon is one where every single one of its interior angles is less than 180 degrees. To put it simply, it just means no angles are pointing back into the shape itself. It's a clean, outward-facing figure, no weird dents or caves. And that brings us right to our first section, the shape of the problem. The real challenge here is translating our human intuition, just looking at a shape, into a concrete set of rules a computer can follow to see its outline from just raw data. So here's the big idea, the core insight. Just forget about code for a second. Imagine you are a tiny person walking along the edges of the polygon. For a convex shape, like our square, you'd start walking, and at every corner you'd make the same kind of turn. Left, then you walk, then another left, and another left, all the way around. It's consistent. But what happens with our dented shape? Well, you'd be walking along, making left turns, everything's going fine, and then, bam! To follow that inward point, you're suddenly forced to make a sharp right turn. And that switch in direction, right there, that's the giveaway. A consistent path of turns means it's convex, a broken path means it's not. Now, this little walking analogy is great for us, but here's the million-dollar question. How does a computer know the difference between a left turn and a right turn? It can't see. It only has a list of numbers, a list of coordinates. It has no eyes, no sense of direction. It's going to need some math. So let's dive into our next section and reveal the secret weapon. We need a mathematical tool to figure out direction, and that tool is the cross product secret. The 2D cross product sounds fancy, but it is the perfect tool for this job. You basically take any 3 points in a row, let's call them P1, P2, and P3, and you run this quick calculation. The result of that calculation tells you, with absolute certainty, if the path you took from the first edge to the second one was a left turn, a right turn, or if you just went straight ahead. So how does this work? Honestly, it's way simpler than it sounds. We just create 2 vectors, or paths, from our 3 points. Vector 1 is the path from P1 to P2, and vector 2 is the path from P2 to P3. Then, we just plug their x and y values into this simple little formula you see right here. That one final number it spits out is our magic turn indicator. And this is the truly cool part. It's not the number itself that matters, but its sign. If the result is positive, it was a counterclockwise turn, a left turn. If it's negative, it was a clockwise or right turn. And if it's exactly 0, well, that means all 3 points are in a perfectly straight line. It's like a mathematical compass for our algorithm. Okay, so we've got our walk-around idea, and we've got our mathematical compass with the cross product. So for our final section, let's put it all together. Time for walking through the algorithm. We're going to apply this to solve our puzzle for real. The logic in the code is actually beautiful. We just loop through every single corner of the polygon, looking at 3 points at a time. For each corner, we calculate the current turn using our cross product. Then we just check if it has a different sign than the previous turn. If it does, say one's positive and the new one is negative, we know the direction switched. We can stop right there and immediately return false. If we make it all the way around the shape without any switches, we return true. Simple as that. Let's actually trace our non-convex example to see this in action. We start with the first 3 points. The turn at the vertex 0, 10 gives us a positive result from the cross product. Cool, that's a left turn. So we'll store that positive direction in our previous turn variable and then move on to the next corner. All right, next up, the vertex at 10, 10. We calculate the turn here, and the result is positive again, another left turn. Now, since our current turn and the previous turn were both positive, their product is also positive. Our check for a direction change fails, so no problem detected. We just keep on trucking. And here it is, the moment of truth. We're now looking at the turn at vertex 10, 0, the one that leads into that inward dent. We run the numbers, and this time, the cross product result is negative. We've made a right turn. So now, our check, cur times pre less than 0, is finally true. A negative number times a positive one is negative. The algorithm has found the dent. Game over.
So really, it all boils down to this one single line of code. This is the heart and soul of the entire solution. It's this simple, elegant check that detects the exact moment our consistent walk is broken, and it's how the computer sees that change from a left turn to a right turn.
So why does any of this matter outside of a coding challenge? I mean, who cares, right? Well, let's quickly go beyond the problem.
Look, if you remember just one thing from all of this, let it be this. The secret to programmatically identifying a convex polygon is just to check for a consistent turning direction. And the secret weapon that lets us do that super efficiently is the 2D cross product. It's a perfect marriage of a simple geometric idea and a powerful mathematical shortcut. And this all brings us to a final thought. This simple check is actually a fundamental building block in computational geometry, computer graphics, all that stuff. So I'll leave you with this question. How could this basic ability to identify the convexity of a shape be the foundation for rendering the complex 3D worlds we see in video games, physics engines, and even Hollywood CGI?